Um, we started down the path of doing big data analytics maybe about a year and a half ago. And we're building this thing we call H2O. It's totally open source. You can find it on the GitHub. Download, pull, and go. What we're building is a platform for doing math where the assumption here is that the data you're doing math on is too big to fit on a single machine. So it's clustered computing or distributed computing, and it's all in memory. So we're doing sort of state-of-the-art in-memory analytics, logistic regression, gradient boosted method, random forest, all kinds of stuff like that. And then the system is accessible in a variety of ways. One of them is with REST and JSON, so you can drive it from a scripting language and the like. And another way is from the Java side, you can directly talk to the big data, and that's what most of this talk is going to be about. Buried under there, there's a KV store that was actually sort of where we started from, but then we realized the key value store market's sort of saturated, and we headed off to doing big data instead. But there's a really high-performance KV store in there, too, as a fun thing. OK, so the core of what we got is a collection of distributed vectors, where a vector is essentially a Java array that's too big to fit in memory or on one machine. So the length of the array is more than an int. I can get at the array elements with the standard fast access you can get on arrays. I'll talk more about this as we go, but it's crucial that the at and the set operators effectively run at the memory bandwidth speeds as fast as you possibly get the hardware to go. Because we're doing math, we have the notion of the missing element, which the math algorithms have long had to deal with. And then we're not talking about fixed size arrays. These are variable size. You can add and remove elements and do things with them. So I have a taxonomy I'm going to talk about for a minute, and then we're going to look at some code. And when I will talk about a single vector, it's a very large vector. Conceptually, it's filled with Java primitives, usually a double. What it's actually done is it's compressed. The compression is often 2 to 4x better than gzip on disk. So you might have an array of actually doubles, but you might have an array of, say, Booleans. Then almost assuredly, it's actually a bit set in memory, or even a run length encoded funky compression scheme if it's very sparse. But if you access the array elements in some sort of linear fashion, you're going to get memory bandwidth speeds out of it. The array is distributed. So here I have my 4 JVMs as an example. I'm keeping the data in the Java heap, and that lets me write Java code that runs fast. And I can write pretty much any Java I want in my inner loops to go manipulate the array elements. And I have to do GC because I am doing it in Java. But because of the way I lay the data out, I actually never see GC issues. We get full GC cycles. They happen. They're usually 1 to 2 seconds on 32 to 128 gig machines. The JVM default GC does the right thing. So I just turn on GC, as big a heap as you can go, and I never see GC issues. And that's because I have very low allocation rates, and I have very large Java objects. Java primitive arrays is the general thing. One vector will hold conceptually one kind of data, but people typically want a collection of these. And so I guarantee that if you have a collection that they're aligned, what I mean aligned is that the data for elements are all going to be co-aligned on the same JVM. So if I want to walk across any row, I'm going to not have to go to a remote JVM to go find that. And that's because typically the vectors represent some sort of real world values like your age or your zip code or what kind of car you own or whatever. Conceptually, you think of this as an R data frame. I can add and subtract vectors freely. I can move them around and reorganize them. And people do that all the time. So it's sort of like a structive arrays model instead of an array of structs. So going across, I might see 100 to 100,000 columns. But going down, I usually see millions to billions of rows. Within any individual column, I have a chunk. This is going to be hidden from people until you dive down into the, I want to be really efficient level of Java programming. Chunks about 1,000 to 1,000,000 elements. It's going to be compressed, but I can decompress in a few clock cycles, typically faster than I can pull it off of memory. It's the decompression's hidden in the cache miss cycle for pulling the next chunk out. And that's the unit of parallel access. And what that means is that any individual thread is going to refer to a series of rows in the same chunk, and they can just walk down the rows in any order they like and do something with them. And that will be running as one CPU, and every other CPU will be doing, okay, here it is, yeah. Every other CPU will do the same thing on their own set. And so I can run all the work in parallel in that way. The nature of the chunks and their size lets me get fine-grained data parallelism out of this thing. So I'll talk about that in a minute, where how we code to that. Mostly you can ignore it, but there's an efficiency hack that people want to play with if you get down to that level. Within an individual JVM, I'm using fork join, Douglas fork joins, and Java 8 now, I guess, for fine-grained balancing. And across the JVMs, I'm doing my own load balancing and my own fork join mechanism. And all the communication and data munging is all handled by the H2O system itself. Okay, so quick summary there. I have a data frames, like an R frame. It's a collection of vectors. A vector is essentially a Java array that's too big to fit on one machine. It's internally broken up to chunks, which are about 1,000 to 1,000,000 elements. Conceptually, an element's a Java double, although its actual representation in RAM it's been compressed, the dickens out of it, so you don't know what it looks like in RAM. But if you go and get me an element, it'll come back to you as a Java double. And then a row will be all the particular elements of a vector in a frame. And the guarantee is it's just efficient to talk about all the elements for one row. One CPU can say, give me the age, sex, ID, car, whatever of some person, and those will all come in at the speeds that you would get them from if you're talking about a plain Java array. And so within this kind of a framework, there's a couple ways to deal with the system. There's the no distribution coding thing, and this will be people who want to use it as a black box for doing math, and we have plenty of paying customers who do that. And these are people who basically say, load a big data set, run a logistic regression, get some results out. Run a random forest, go score the data set, build me a model, hand me the model, I'm going to go put it in production to go do something. I'm trying to do high-speed credit card fraud scoring. I'm trying to do risk analysis of my whatever, healthcare, insurance, whatever it's going to be. And then there's the next layer down would be I want to do some sort of data parallel coding where I have a data set that's too big to fit on one machine, and I want to speed up how I'm dealing with it. I know what kind of math I want to do, but I'm not a systems engineer, so I want somebody else to handle the systems engineering of a distributed cluster for me. And that's what I'm going to talk about in here. Most of that's done with a MapReduce style, and basically anything that looks like dense linear algebra falls into that category. And then you can do more complicated stuff. Any of the graph algorithms will go down in there. So now I'm going to talk about the API. And I'll preface this by saying I've been trying very hard to stay away from defining a language. And I'm sort of got my back against the wall, and that I've gone as far as I can go with Java. And it works, but it's clunky, and I need a better language. But I have a really fast, really nice back end. So I'm looking for the right language to plug on the front end. That said, this is where the Java API looks like. And so the basic paradigm is map and reduce, where when I say map, it's not the Hadoop MapReduce. It's a theoretically clean map. So it's a map from type A to type B. And reduce takes two type Bs and makes one type B. So within this is my type A. It's a double. My type B happens to also be a double in this example, but it could be anything I want. And reduce takes two type Bs and makes one type B out of it. In this case, sum of squares is done in this many lines of code where I say, make me a new MapReduce task. The map call is going to return the square, or the reduce is add them up. And then I say do all, and I apply a vector to it. And this will run just like that at memory bandwidth speeds across a cluster. So milliseconds per gigabyte of data kind of speeds. I can have more complicated things, including things that have state. Here I've got a couple things I'm going to sum of x, y squared. And my map call does something a little more complicated. And my reduce takes a this and a that, and the this is implicit, and the that is same type as the object I began, and it merges the two types. So this is type A is this pair of x and y, and type B that comes out is the LR pass 1. And then the reduce takes two LR pass 1s of this, which is implicit, and the that, which is handed in, and folds them together. And again, 6, 7 lines of code, I got something that'll run parallel and distributed across my cluster. I was mentioning chunks as the unit of parallel access. It turns out that the prior slides internally are wrapped by a for loop that runs over a chunk at a shot. In this case, I'm going to say for all rows in a chunk, and I do my chunk at, and that is where the decompression happens. Those at calls will do the right thing to convert a bit set or a scaled, biased offset or just a plain old double into the right thing, and then I do my math just the same as I did before, and reduction just the same as before. At this layer, I can see the for loop, where this loop's probably 1,000 to 1,000,000 iterations. And if I want to do any sort of loop invariant optimizations, I do it here. I'm going to get the efficiency you'd expect out of hoisting something out of an inner loop. But if I just want to write my code like this, I don't need to worry about that. Within this paradigm of MapReduce, I can do a bunch of things. It's more flexible than I first thought when I started coding in it. For instance, here's a filter and count for people who pass some particular filter, add one or not, and then reduce. This again will run parallel and distributed across the cluster and tell me how many underage males I have. I can return the underage male set. Oh, the colors are all gone. Fine. By simply making a new kind of vector that is the result output vector. And here, the append call is going to throw in people who pass my filter into it. The output vector is too big to fit in one machine, so the output vector is distributed as well. When I write the accessing to it at the Java level, I say make me a new vector, do my do all call, and when I get done, I immediately can go use that vector for the next step, the next piece of math I'm doing. But I didn't actually return this result to one machine, to this machine that was driving this, because the result's too big to fit in memory in that one machine. So that's a distributed output. The calls I was doing with the sums and sums of squares of things, that's a small result. And I can get returned back to me one small result, the POJO and the reduction, and any number of large results that are all separate output vectors that represent results that I'm writing to for any one pass over the data. I can do some other stuff here. Here's a GroupBy. Let me back up here and talk this through a little bit. In the GroupBy, I'm really saying I want to count of cars by age. I want to break people out by their age and their car type and get a histogram on them. And I have some array that I'm doing a plus plus on. And so let me talk through this a little bit. Because car ages here is a new call done inside the map, this is guaranteed to be local to the thread that's running that particular map. And that means it's an output field, and it's private per thread, and therefore it has single-threaded access. So this plus plus is not synchronized. It's exactly what it looks like at the Java layer, but it's thread safe, data array safe, because it's running single-threaded. Also, because it's an output field, I have to reduce it. And so I have a reduction that has to run over the array and add the this and the that. And again, this is going to run single-threaded. And actually, I have a utility for adding arrays like that. And so the actual output call just says something like utilities, add arrays, and it's done. Here's another one where I have a distributed hash set, counting uniques across the cluster. I can run through some particular data set here, my visitors. They have some sort of ID that they want to get used. I pull up my visitor ID and I throw it in a hash set. The reduction is just add the this and the that, doing a put all operator. And this will give me uniques across the cluster, again, at a rate of milliseconds per gigabyte kind of thing. The thing that's different from this call, from the prior one, is that I have set the Java element here in the constructor instead of in the map call. That makes it shared. Shared things are mostly read-only or usually read-only. This one happens to be written to, so it needs a reduction. But if I had some sort of large array of constants I wanted to hang in there, or some fixed POJO, it would be treated as read-only and shared within a node, but obviously replicated around the cluster as needed. Okay, so mostly I'm winding down here. The big high-level summary here is that most simple Java in those inner loops just works. And it runs at the full Java speeds. Reads in particular are as fast as plain Java array loads for arrays that are too big to fit in memory. Writes are a little bit slower because it will compress behind your back, but I'm typically memory bandwidth speed limited. You can do conflicting writes into parallel arrays, for instance, and that'll run slower, but will follow the strict Java memory model results. I do support transactional updates, which we didn't show in there, but that's done by all kinds of internals in the system doing transactional updates on keys for all kinds of control logic. That's mostly it. We're writing big data analytics right now. We have a bunch of state-of-the-art algorithms implemented. Running distributed, running really fast. We work easily on 100 gig data sets. I guess we're testing nightly on 100 gig data sets, and we've done terascale work in-house already. And we have paying customers, so come play with it.
There we go. Time for questions, and I'll ask the first one. What about, say for the terascale data sets, what happens when the data set does get too big to fit in memory across the cluster?
So we're geared to handle data sets we can fit in RAM, but we'll spill to disk as needed. And as soon as you spill to disk, you're typically now limited to every pass is going to reload from disk and then spill again behind you. And you're back to the Hadoop style speeds. It's 100x slower to spill to disk. So we'll take it, it'll work, and it'll be 100 times slower because you're not getting the in-memory speed. Yeah.
Do you care about sort of numerical accuracy or so? So for example, if you have a really large data set and you do the summation like you did, you would probably lose a lot of precision at least in some cases.
We're doing lossless compression. Is that what you're asking?
Well, no, I mean just like if you take loads of numbers and you add them all up, and some numbers are big and some are small.
So the actual algorithms that are written, however people want to write them, do whatever you say. Some of the algorithms you write can be more numerically stable and some less. So for instance, there's a way to do average invariance using the recursive mechanism that's a little bit slower to execute but is more numerically stable. And wherever those choices are made, we always go for the more numerically stable kind of option. Still, if you add a billion tiny numbers up, you expect round-off error is going to kill something. That said, the nature of the log tree rollup is such that you don't add a big number to a small number very often unless your algorithm is designed to write that way. Like if you sum all the numbers in a chunk, that's not so many numbers that you expect a huge amount of round off. Then you sum results of chunks together in the reduction phase, and again, now it's bigger numbers being added to big numbers. So it's more numerically stable.
Yeah, I mean, you sort of get some better numerical behavior by the fact that you sort of distribute the reduces by the chunk size automatically, as you said, but
we're using the numerically stable versions of these things if there exists one.
Right. Okay. Thanks.
So not all algorithms have a variant that's more or less numerically stable either.
I know I have a couple of questions. The first one is how do you distribute the data? I mean,
okay.
So how do you load the data onto there and decide how to slice it?
Yeah. So we load the data from any number of data sources. I kind of shortcutted that. HDFS, S3, local disk, NFS, whatever the hell you want. When we load the data in, we'll do an initial distribution based on a pseudo-random hash. So we get reasonably good distribution out of it. It's not perfect, but the point of pseudo-random is it's never the worst case one either. Instead, you get average good behavior out of it, which is what we end up seeing all the time. That said, once it's distributed.
So where's the, I mean, I envision those linear arrays, right? Where does the hashing happen? Could you explain that?
When I load the data in, I'm going to break it up in chunks and then pseudo-random hash it around.
Okay.
So the usual thing is that I'm reading a CSV file, which is already a variable length text encoded thing. It's probably a gzip CSV file. So I'm busy doing a parallel parse of a gzipped CSV file. Every individual CPU ends up with a wad of rows of data, and he's talking to his neighbors about how to handle the edge cases and crap like that. Once that gets done, and with a pile of chunks of the compressed version of each of however many rows I had, I usually at that point say, hey, that's good enough. I'm going to leave it right where it is if the CSV got striped around the cluster. Now, the initial striping of the CSV is just done by, taking 1 meg chunks and handing them round robin around the cluster. So there is a pseudo-random hash function thrown in there to make sure things get spread right. And right after the parse, there's an initial load balance. After that, the data typically doesn't move. It's too big to actually do it all everywhere. The load from disk is way slower than the network traffic, so you never see the pseudo-random hash distribution pass. It's there, but you don't ever see it.
So the effect is that the blocks are not really sequential like you're showing.
No.
They're like all scattered.
Yeah.
It's in random order,
Yeah.
essentially.
Now,
the
I
blocks.
say that they're not actually sequential, pseudo-random. In order to help with the goodness of life and everything, there's actually chunks of like 16 in a row are going to be pseudo-randomly guaranteed in a row. Like statistically, they're highly likely to be in a row. So if you have an algorithm which is doing an edge case thing, where I'm talking about my row and the one before and the one after, then as you walk this stencil down and you step off the end on the left and the right, you're almost surely hitting a chunk which is local to you anyhow. But there'll be some edge cases where you'll miss. It's a KV store with caching. The data gets pulled in locally, and the next time that algorithm runs, you won't take a network traffic. Now, I just said I pulled some data locally and cached it, so you're replicating data. Because you're statistically likely to only replicate one chunk on either side of 16 in a row, I just replicated 10% of the data, which I can handle, right? If I striped it perfectly around, then every time you step either left or the right on the end of a chunk, you'd replicate the entire piece, and suddenly you double your data size. And then you can't do that. It's already too big. Right? So yes, that's been thought through. That said, you can still do a random access of any piece of data from any node. It'll all get pulled locally, and you'll drown the one node in data. I'm sorry?
Yeah, all the chunks.
Well, if you go from here and you step up one, you pull, this guy's local, so it's good. If you go here and you go up one, you'll pull that chunk here, and you have a copy of it here. So you have to watch out for this. If one guy is talking to every row just at pseudo-randomly, he's going to pull all the data locally and drown in it. Now, going across, I guarantee that they're aligned
So can you,
in that way.
so a typical application, I don't know if there's other people that have questions, so I mean.
Well, somebody else has got a question. Let's go around. We'll come back around, and then I'll break into a demo here. But let's go around once more.
Do you do anything to handle straggling kind of jobs? So if you have like JVM3 is running a lot slower than kind of the rest of them. Do you do anything to kind of compensate for that, or?
Right. So I don't, and I don't see the problem either. So my intent was always to do load balancing across the JVMs the same way as fork join does load balancing within a JVM, but I almost never see that as an issue. I really do have good distribution of the data, and then everybody does about the same amount of work, and I don't end up with stranglers.
So I was just asking because it can be an issue in some latency-sensitive situations, but I guess you're aiming more for throughput than latency.
Yeah, I'm typically aiming for throughput. That said, I can do a lot of stuff really low latency that's sort of like a key value store put or get is about 150 nanoseconds, much faster than network time because I can cache everywhere. Scoring on these models is usually, if you build a model and you want to score it, the scoring cost is usually totally dominated by the network to get your data into the model and back out, and is not an issue. If instead the question is how fast can I build a new mathematical model, or ask uniques of visitors in the last 10 minutes or 5 minutes or whatever, typically I don't have timing issues that run beyond a few minutes. I'm looking at, my latencies there are seconds to milliseconds. I don't care. It passes 10, 100 milliseconds over 100 gigabytes, and then I don't care now.
Given the nature of what you're doing, have you ever found yourself wishing you had access to SIMD instructions on Java?
No. Yes and no. It could pay off, but I don't want to deal with it. I want the JIT to deal with it. Most of my inner loops, the hot ones, really do look like go load something and decompress it and then do a little bit of stupid math and go to the next one, decompress, do stupid math. The decompression varies by chunk, by chunk, by chunk, but it's always something trivially stupid. That said, it would make sort of very ideal for a SIMD to take a wad of bytes, spray them across, add a bias to them all, shift, scale, whatever it's going to do, and then do parallel at a time. And it's all obviously, I mean, I've carefully arranged it, obviously available for the JIT to go do. A little bit of unrolling, the JIT could do it. I don't know if the JIT does it. Now, having said that, what I see is I look like I'm memory bandwidth bound. So that having the inner loops go faster won't help unless you can feed them. So I'm more interested in a better compression than I am in a better, faster inner loop.
Okay, I just think because like Haswell's now going to have fuse multiply add, and you can basically decompose everything down to that the way Fortran does.
Again, I'm down to I can't feed it fast enough. So I want to have a better compression. And now I want the fancy instructions on decompressing. As I'm going to load a cache line, and it's going to have 8 or 16 or 32 actual values in there after decompression. And that's what I want to have fast now. Right.
Do you have any? Do you address the resilience at all? I mean, if you lose a machine in your cluster, what happens to it?
No. So we talked about that for a long time. The company decided not to go there. So this is a cluster that assumes that you have a data center that's like functioning well. If machine goes down, you lost it, and you have to restart the cluster with one fewer members and reload your data and go again. Right. So I'll assume your network is flaky, but I'm going to assume your machines are stable. Right. So the mean time to failure is mean time to machine getting lost. So this is not a store. There's no data loss. You just have to reload. It's like a big calculator. You reboot the calculator.
Thanks.
I was going to ask the same question, but another one would be, what happens if we have updates, concomitant updates on the same data set?
So where do we go with this one? So the actual KV store side of things, the data is all kept in the KV store. If you go right into one of these big arrays, within a single thread in the map call, that's guaranteed that those rows will be single-threaded access. That will run at memory bandwidth speeds and give you the obvious correct semantics because everyone's writing to an independent value. If you're having colliding writes to the same value, then you fall back to the Java memory model semantics, where you're getting synchronization guarantees. Unless you ask for it otherwise, your synchronization guarantees will only be at the edges of a MapReduce, of the entire MapReduce pass, which is to say you don't get very strong guarantees. Somebody's write will get lost. Same as if you have an unlocked racy writes to the same shared variable.
Got it.
You can ask for locking, synchronization if you will, and then it will slow. It will go slow, and you won't lose any writes.
So my question is, you have a cluster, you've shown code where the map and reduce are in the same file, basically. How does the code to run get distributed to the cluster? Do you assume it's already there, or?
When you launch the cluster, you'll launch it with a jar file. So it launches with java-jar h2o.jar. That got the code around. Every node in the cluster had to come up with that java-jar. And so the code all came there. So the code's been distributed at that point. That said, we've had working in the past, and we'll probably get working again, would just pass the jar new code around and do class rename on it, like it's another chunk of data you're just passing around the cluster. So we have done so. It's currently not in there because no one cares for it. Okay. But you're writing code to a cluster that's up already, and you're expecting the cluster to stay up so you can keep adding code to it. So I can launch a cluster in a handful of seconds. And I just did. You missed it, but I've already launched a cluster on my laptop. It came up in about a second. And I'm going to play demo games here. Actually, I'll do this here first. So here's a cluster of 1. Let me get a cluster of 2 going here. I might be happier. Okay, so I have a cluster of 2 going. We do java-jar to launch. If you don't specify otherwise, we'll use multicast to find other members who've launched with the same default name. I think my my default's my username here. So the cloud name's CliffClick here. Within a room full of people with laptops, within a meetup, within my own data center, multicast, bang, I got a cluster. It takes seconds. For happy IT people, we'll take a flat file and we'll only talk to those nodes if you want to do it with a flat file. So people can put up in data center, know exactly who's talking about what. Having got a cluster up, I'm going to pull some data in. What we got here? How about UCI cov type? So here's a common data set that's publicly available called cover type. Cover type is a forest cover, whether it's alpine meadow or pine woods or mixed hardwoods or whatever. This particular data set has about 500,000 rows. After pulling it in, and 55 columns. After pulling it in, I have about 10 megabytes in RAM. Here are my columns. It has no headers because that's what the data does. Min, max, mean, a bunch of other stuff's pre-computed on load in. Here's my 55 columns going across, and going down. So there's a bunch of Boolean columns here. The column on the far right has numbers from 1 to 7. That's the min and the max from 1 to 7 there. That is the cover type of one of 7 different cover types. Down on the column 0 is the meters above sea level and elevation, distance in meters nearest water, and there's a bunch of other features going on there. I don't know what. From here, I can go get a bunch of algorithms. We'll pick, I don't know, GBMs, find one. We'll go run this thing here. So this is the web interface. It said you can control it with REST and JSON. The web interface is basically pretty printing of the JSON. So everything you do on the web, you can do in the JSON, and this makes for a nice, easy demo here. So I'm going to do prediction on the forest cover type. I'm going to keep all columns and take all my defaults and just hit go. And then somewhere in here, let's go back. We'll go here, get this going. Okay, so cluster status. Oh, it's Windows. I don't get system load. Here's my data keys and the key value store says it's distributed around. I'm watching memory getting used, and I'll run through GC cycles and a bunch of things going on there. Meanwhile, back over here, he's busy, well, as he crunches along. Okay, so fine. Let me turn off automatic polling. We had a chance to look at it. So I'm building a model here. The model is, this is a gradient boosted method, but the model is predict the cover type based on the other features. This is called a confusion matrix. Going down is the actual cover type. Going across is the predicted. Correct answers are on the diagonal in green. Errors are on the off. And it's the nature of GBM that it will make a bunch of passes over the data and slowly build a model that will eventually get very, very accurate, but it's quite a slow model builder. And furthermore made slower by the fact I'm running it with 2 different JVMs on my laptop. So my laptop's like, fan just kicked in, and it's an older laptop, and so it's busily like crunching away. And every other pass, it has to swap data back and forth between the JVM, so it's opening network sockets and talking to each other and doing all kinds of crazy stuff here. And it's going to be a while. It's up to 4 trees or 5 trees, and it's back to pulling automatically, and will drive you nuts because it forces the screen to flip around. I don't know, so that's sort of an easy thing here. Other stuff I can do with this guy, download the files as CSV and grab some summary data off of things, and let's see how this is going to fight with my GBM here. There it goes. Okay, so I get, top 5, bottom 5, 0, standard deviation, histogram, percentiles of everything. It's basically doing math on vector by vector by vector. So that particular example data set is at the very limits of what you can do with like R on a laptop. It's technically doable, but I'll do in a few minutes. It'll take R like all day, like 12 hours or something. This is a good 100 times faster than R for doing this kind of stuff.
So at the upper end of the data sets that you're currently supporting, what would that cluster look like? Like how many nodes, how much RAM? That sort of
Right.
thing?
So we do better with fewer, fatter nodes, but we'll do fine, 16, 32 node clusters. So a common one for us is to pull in all the airlines data set for the last 30 years of airline flights. It's like 120 it's 120 gigabytes of data, something like that. And there's 12 gigabytes of data, 120 million rows, 12 gigs of data. That one pulls in on a 16 node EC2 cluster of like modest size, comes in like 2 or 3 minutes, and then runs a logistic regression in like 90 seconds or something like that. To go to a terabyte, each of those nodes would have to be 64, 128 gigs, something like that, to get to a terabyte data set. And that's actually pretty reasonable. Machines we have in the lab, we have 4 machines of 256 gig, so that's our Tera cluster right there. They're fairly modern, but nothing special, x86s. Loading in Tera set data size is how fast can your MapReduce spindles run. It's all disk I/O bound. Once it's in RAM, the logistic regression on that is, it's 10 times more data, so it's 10 times slower than the 90 seconds. It takes a couple minutes to go get a logistic regression on a data set that size.
Any other questions?
Yeah.
Well, it's enticing because one of the things that all the graph databases, have you tried to run anything like graph-like or graph-like algorithms? Because it's most of the graph databases like Neo4j is known to be really nice and fast as long as you stay on one machine. But maybe a model like this would actually suit like graph-like
So we've
things.
long thought about graph database, graph work, and how would you do it? And my thesis here is that the KV store lets me cache things at the perimeter of whatever region. So if I distribute my algorithm in a way that I'm walking around the center of some piece of graph, and this node's walking on the center of that piece, and this guy's walking around the center of that piece, 4-node cluster like that, at each of the periphery, I have to talk to the neighbor. The KV store will keep that straight for me. It'll cache locally, and if I don't do any updates, it was all free. I just cache the peripheral. So I have a center ring of graph I'm touching. I have an annulus that I have to cache locally that I'm not doing anything except reading from. And when I have writes with my neighbor that were conflicting, the KV store will straighten that out. Having said that, I think it would be efficient. I haven't actually implemented it, so I don't know. I think all I have to do is have heuristics on the walkers to say walk in a centralized region and don't get too fancy around the edges. Don't worry too much about the edges, not the KV sorting it out. As long as statistically you're likely to be talking or working with things that are inside the innards of your cached local data, you're going to be fast.
You don't have an API to ask whether the chunk
Yeah, I do.
is
Yeah, I do. Yeah.
You might want to have a
Yeah.
algorithm that goes as far as
Exactly. No, and that's how all the other algorithms do their thing. That they say, take all the local data and do my pass on it. So when I do GBM here, he does a bunch of passes of the data where he has to build a decision tree at each layer, and he goes and fine-grains. So each pass is build a histogram over all the data split by whatever the tree looks like at the moment. And when I say make a pass over and split, what it really means is the owner, the leader, says to his two neighbors, hey, go do this thing. And they tell their 2 neighbors and so on in a log tree breakdown. And then he says, I take my own local data, do this bit. And they all take their local data, and then they do the roll up in reverse, doing the reduction step by step by step, until it rolls back to the leader that way. So everyone does local work, plus the reduction work is done as a log tree roll up.
Anyone else? All right, let's thank our speaker.